So, I am giving the last two lectures, and I will try to stay away from being too technical in these last two lectures. We have covered many different concepts, and the goal is to bring some of them together and also to give you some motivation what you have, many of the stuff that what you have learned, what it is good for. I have chosen one underlying theme to illustrate some of the techniques, and also you learn some new algorithms in the next two lectures. But I think this is something that is becoming increasingly important, and there is and in many different communities, research communities, you will see research papers in various conferences on these topics. So, one way to motivate it is that suppose you want to create a virtual world or virtual physical world, whether it is on the internet or the many other applications that Army is very interested in doing it for training exercise, also government and commercial entities. So, if you want to build a virtual physical world, then which consists of has very lot of different geometric objects, and then of course, there is much more to it than just pure geometry, but since we are focusing on geometry, I want to talk about the geometric aspects of virtual world. So, first question is how do we put the things together, and the way they are done is basically what we have in the physical world. You have various sensors, you have various measuring devices or mapping devices, we use them and try to sample them. So, examples sort of vary from, let us say, 3D model generators, and for example, there is, I do not know if you have heard of it, I have mentioned in this class also there is something called LiDAR technology. So, what you can do is either in the aeroplane or in some either vehicle or ground vehicle, you can put a what is called a laser finder. What it does is it sort of sends a laser scan and it gets a laser back, and by the reflection the distance can figure out how far it is, the object is from where you are. It is like radar, but it is a laser frequency laser stuff. And in different forms this is being used a lot to generate 3D models. Okay. So, for example, so for example, like just to give you an idea, the latest version of F-16, which is one of the US fighter planes, is going to have 8 video cameras and 4 LiDARs to collect so much data. Okay. And what you want to do, you fly over enemy territory, you collect all the data, and once you have done few times, you have collected very high resolution 3D model, and for them it is very important, right, to have the 3D model, then you can plan and figure out how to do battlefield management doing it. Now, this is a military application, but you can think also very commercial applications or civic applications. For example, more and more what is happening is whenever you have disaster zone, you send tiny robots which have laser finders. They go and explore the 3D world there, which is the damaged area, and then you figure out what is going on there, and then you can do the rescue mission much more effectively than sending human beings, and they cannot reach all those places. Right? You can think of various many applications in the commercial world. For example, all the new airports that are being built, first you build a very detailed high resolution 3D model. That is true also for planes. For example, Boeing 777, which was designed to a single wire level, the digital model was built before anyone started thinking of manufacturing it. So, all these sort of basically what is happening, you are building this huge 3D geometric models and the geometric virtual worlds that you are developing. So, what sort of question comes is how do you assemble such a world? Writing, composing any music, right. So, first you have notes from or text, you have letters, words, and and you have a hierarchy of representation where higher and higher level of abstractions, and the same thing happens here. Then the question comes is what is the hierarchy there in this geometric representation. So, I will not be able to address all those questions, but I want to touch upon some of these issues that one has to deal with. So, the first thing comes is that how do we start with very basic objects, and then you build a database of objects, and once your database objects you can club them together and then start building more complex objects. Okay. So, there are various things that you need, tools that you need. One is how we represent an object, 3D object, or represent a shape, and then we build as and then you need a hierarchical representation of these shapes. The second thing you need is how we compare two shapes, right, because you want to talk about like, okay, I need this shape, I need that shape. You need some mechanism so you can compare two shapes. Like for example, in dictionary, when you type on Google word, you type some word and then you get something like compare the two strings, right. Same thing, you need to do some model for some way of representing shapes, or sorry, comparing shapes. Now, once you have compared shapes, the next stage comes is you want to classify shapes, that all these objects are similar, like clustering, right. So, you want to do cluster 3D objects. Then what comes is that basically is searching what is called indexing databases, that you may have some database. Now, I am trying to build a world, I need some object like this. So, but you do not want to give the whole representation of the shape, you want to give some keywords, right, and then you want the database to search and give you the objects which represent to some words. Now, existing data, most of the databases, you type a word and then gives you the shapes of which word. The ability to search in the 3D world by sketching a 3D object and say return with objects that are similar to this, that is still in infancy stage, and none of the commercial products give you do a very good job of doing it. So, this is also called what is called the visual information or geometric information. How do we build this geometric world? So, in these two lectures, I want to give you some very basic sample of very few of these questions and give you some idea of what is being done there. Okay. So, let us talk about the very first thing, the shape representation. So, the very basic stuff is that suppose you have some device, either you have a laser finder or some other way of measuring or sensing device. Then the question is you want to sample. What you do is you have, let us say you have this room, you put a laser finder here, you will scan all around and you will sample points. The first question comes is how densely should you sample, right? That is the first thing question, sampling question comes. Like for example, all you know, if you take any course of signal processing, is called that if you want to reconstruct the signal, then it has to be twice the frequency, highest frequency to reconstruct our signal back. So, what is a similar notion in this case, geometric world, that how densely you should sample, okay? And that basically leads to, so first let us talk about sampling. So, how densely okay, and even this very basic question is not fully understood, and I will not give you all the technical and what is the best result, I just want to give you an idea what happened. And this is closely related to the notion of Voronoi diagram that you have seen. Okay. So, there is something called medial axis. So, let me basically give you some idea. For example, suppose you have an object. Intuitively, without sort of being mathematically precise, you do not have to sample, okay, I should do it here. Okay. So, intuitively what is like in this region, you do not have to sample too close them, right, you can get away with the sparse sampling. But when you come to this region, here you have to sample very densely, because if you do not sample densely, you will not be able to construct whether the object looks something like this or you have something like this shape, am I right? Because if I just give you some points like this, then you do not know whether the curve is going something like this or curve is going something like this. So, you should be able to distinguish these two. So, question is how do we distinguish these two cases? For that I need the two notions, what is called the medial axis, which is generalization of Voronoi diagram, and based on that there is a notion of what is called local feature size. So, So, medial axis, so we Warnow diagram, the way, at least the way I had defined in the class, I defined it for a finite point set, and you can think about medial axis is a generalization for an infinite point set for curves or for other shapes, surfaces. So, let us look at, suppose you have this let us call object this, let us say this shape I have P. If I take a point inside, take a generic point inside this X, and I start drawing a disk centered at this point X, right. In the beginning it will be empty, it lies completely inside the object P. As I increase the radius continuously, it will start expanding, and at some point it will touch a point, boundary of the P, am I right. Now, if I do it from generic point, what will happen? It will just go and touch at one point, but there will be some points inside that. If I do this, it will touch 2 points, right. For example, so if I take, let us say I draw it here, let us say if I start increasing the disk, it may touch this. Okay. So, the points where I will not define again, one can make this notion more mathematically precise. So, we can talk about what is a limiting ball, what is the smallest empty ball, which is, or the smallest ball at which it touches the bound, it touches a boundary. If it touches a boundary at 2 distinct points, that point is said to lie on the medial axis. So, medial axis of P. So, I will define for this ball as a Bx, just notation. So, it is the smallest ball centered at X that touches a boundary. Okay. So, Bx let us say boundary of P. Okay. Medial axis of ball is of P is a set of point X such that if I take the Bx and I take the intersection with the boundary, it is greater than 1, right. So, it is a, I will not prove it. If you draw the medial axis, it will be kind of one dimensional network. So, it will be basically what will happen is it will look like a something like this. Okay. So, this is, if you think about the Warnow diagram, if you look at the edges and vertices and look at that sort of relates to the medial axis of a finite set of points. Okay. And here that is what you will get some it will, if you have simple polygon, which is the case, or like boundary or is simply connected, then what you can argue then that the medial axis will be a tree. So, if P is a simple polygon, if P is if delta P is connected, then medial axis is a tree. Okay. Does this make sense, or any questions about the definition of medial axis? Now, it is not easy to compute medial axis. Now, in 2D it is not too hard. So, if it is a polygon, you can compute it. Now, if it is in algebraic arcs, it starts becoming more complex. But this notion that I defined of medial axis is not only in 2D. If you have a surface, some shape, 3D object, you can define the medial axis. And there the problem is still open, how fast you can compute the medial axis. And there is no robust algorithm. So, that both theoretical problem that is still open. How fast you can compute a medial axis, what is the best known algorithm. Fine, I do not care if you are a practitioner, you do not care about the worst case running time, but you need a robust software to compute medial axis, and that is still does not exist. All the basically works, basically what they do is they do some kind of a patchwork at some level. They compute up to some accuracy and then they do some heuristics, patch it, and they do not compute the exact medial axis. And the reason being that even if you have a polygons, polytope, let us say some piecewise linear formed by triangles, the medial axis may consist of bicubic patches. As a result, the algebraic complexity, the bit manipulation you have to deal with, that becomes quite a nightmare, and that is a challenge. Okay. So, that was a slight detour. Now, if I have the medial axis, then what you can do is for every, there is something called retraction in mathematics. If there are no sharp corners, if this shape is smooth, mathematically smooth means that if you think as a curve, all the derivatives exist, then what will happen is that there is a, for every point on the boundary of the polygon, there is a unique point on the boundary axis, so that Bx will touch that point, right. So, what you can do is you can do a one-to-one mapping from every point of the boundary, you can map it to the medial axis. That is what that means is that if from that point if you touch the boundary, draw the ball, Bx will touch at that point. Okay. So, retraction, that basically if you want to define the phi is from P to the boundary P to the, I did not use a notation for medial axis, let me call it M, then phi of P is x if Bx, oops, if P belongs to Bx, okay. Right. So, that if it is a mapping from the boundary to it. And the local feature size, which is denoted by LFS of P, is equal to the distance between x and P and phi P. So, that is a distance between the medial axis to the point, so where it retracts to. And now, if I go back to here, if I look at the, what will you notice is that the local feature size here will be is pretty small, because the medial axis will pass through here, and the places here the local feature size will be quite large, and that is a reason that I have to do the sampling denser here, and I have to do this. So, what is known is that now so the sampling density, as you can assume, is inversely proportional to the local feature size. So, where you have a local feature size is small, you have to do dense sampling. When you are away from local, where the local feature size is large, you can get away by sparse sampling. And this is a basically question where you have signal, when you have high frequency components, you have to do dense sampling. When you have local small frequencies, then you can get away by doing very sparse sampling. So, that is a sort of yeah.
So, this sampling density and local feature size are defined for each point P, right?
Yes.
So, now there are potentially infinitely many points. So, at which point I should evaluate this thing? And
very good question, very good question. So, that was sort of that was going to come, I was going to come to next is so if you want to be very conservative, you compute the minimum value of this, am I right? So that is the maximum density you need to do. So if it is a signal, so again you ask a question when your signal is coming, at what frequency I should sample, and if I know what the maximum frequency is, then I can be safe, a conservative, and I sample at that frequency. So what sort of so before I answer your question, let me put your question on the table. Let me just sort of make another statement, and then I'll answer. I will elaborate on your question. Now, why is, again I will not give you the proof, which is much very technical, but let me give you intuition why that is the case, why this makes sense, why does this statement make sense. Here is an intuition that suppose this is your, and if you did the sampling, and suppose you compute Delaunay triangulation of these point sets. Okay. So let us say what I did was to sort of address his question. What I will do is, suppose I knew the polygon. Of course, that is a chicken and egg problem, because I do not know the polygon, that is why I am trying to do the sampling, reconstruct it. But suppose I had the polygon and I did the someone or some oracle told me what you have to sample at least at this density. So suppose I know what is the smallest local feature size of this polygon, and with that keeping in mind, I did the sampling with the, let us say, enough density so that local feature size condition is met. So I done dense enough. Now I computed Delaunay triangulation. Actually, what I am saying is not quite true, but that sort of gives the intuition, because one has to be more careful than what I am saying. But suppose I computed Delaunay triangulation of these dense point sets. Then what will happen is you will have edges, you will have all these edges, because if you can convince yourself that if the density is small enough, these edges will, there will be empty ball passing through these 2 points, basically look at diameter. But then there will also be some cross edges, something like this. But the way I have chosen, the way I have defined the local feature size, because what you know is that there is an underlying medial axis passing through this. Okay. And the way the local feature size is defined, the length of this edge will be at least twice the local feature size, and the length of these edges will be less than the size of the local feature size. So what you can do is you can throw away all the edges which are bigger than the local feature size, and keep the ones whose size length is smaller than the local feature size. Then you can basically, what will happen is you will, if you do that, you will reconstruct the shape back. Now I should say, again caveat, say what I said is not quite true, because one has to be more careful, because if I do what I said, I will get some spurious edges. But that's sort of, those are technicalities, but that's the idea, and that's how you reconstruct the shape. So what you do is you do the dense enough sampling, you get an estimate what the minimum local feature size will be. Based on that, you decide your sampling rate, and once you have sampled, have got dense enough samples, then you compute the Delaunay triangulation and keep this right set of edges, the small edges, and throw away the long edges, and then you get the shape back. Okay. Yeah.
Will the medial axis be always continuous?
Well, medial size, yes, medial size is a connected network of this one, yes.
It's not very obvious.
No, it's not obvious. It's not obvious. One has to sort of argue. Now, in order to do that, I have to sort of make some assumptions, because so the way of thinking about it is, if you think about this point set, this curve as a infinite dense of point sets, just think of the point set. And the Voronoi diagram, when you look at the Voronoi diagram, then if you look at the edges of Voronoi diagram, they form a connected, right? And you just so if you, what you do, the way you argue is that you sample points and then you take the limit, because what you know is that if this is a finite point set, then the medial axis is connected. and then you keep on just taking the limit and you reach it, it remains connected. But you are right, it is not, it requires a proof, it is not obvious. Okay, so that is basically, that is how one does it. Now, this is a small polygon. For example, there have been a number of projects. There was a project at Stanford. What they did was they went to Italy and scanned through laser scanner. They scanned all this old sculptures, Michelangelo sculptures, David, and each of them had billions of polygons, points, because they had to do, because if you have seen those sculptures, they have quite detail, am I right? They have hair, nails and toes and all the details. In order to capture all those details, they had to sample very densely. And now if you have billions of points and you have a compute, you do it, so output size has huge size. And if you want to do any processing on them after that, if you want to do interactive walkthrough in such a museum which has all this virtual museum, it is going to be very slow, because rendering all those billions of polygons for each of them. So then what the question you would like to ask is, okay, I did this, now I reconstruct the shape, and there are precise statements that one can make. So if you know, if some of you know any algebraic topology, then what you can sort of, the statement one can make is, the algorithm I described with some caveats, the shape that you get is homeotopic to the original shape. It means the structure will look like the same. And you can also measure that if you, how much sampling density you did, you can also say that how much geometric error you will have, because if you have done the density this much, so you will not get the actual curve back, but you will get a piecewise approximation of that curve of the shape, and the error will be at most epsilon, and you can define what the value of epsilon will be. But it has too many points. So, next step, and that is again the topic of the whole research and active research, is can I thin away some of the points, because this goes back to the question he asked, is that local feature size is different in different places. So, I do not need to keep all the points, because I did the density sampling with respect to the smallest local feature size. So, the places where the local feature size is large, I should be able to throw away some of the points. So, that leads to the whole area what is called curve simplification or surface simplification. So, for example, this very different application where that is being used a lot is the following. Is now every car has a GPS, like your cell phones have GPS, and you can sort of be easy to track people, right. So, you are, and the GPS you want to again want to sample very densely with the GPS, your position. Now, if I connect them, I get a trajectory. Now, unless the trajectory is very changing a lot, if the trajectory is more or less the same, there is no reason I need to keep all the points that I sampled. I should be able to throw away most of the points. So, I do not know if it is happening in India, but I know that for example, many European countries and US, what they do is that there are a lot of people who commute a lot on the cars. Every sort of day they are commuting and they are going in the same pattern. Now, the question is that you want to do a road network, generate a road network, and you not only just want to get the shapes, but you also want to know what is the congestion on the stray, what is the speed limit on average at during different type of daytime. You want to get very detailed knowledge. So, what they have done is they have basically people, I will pay you some money, since you are going, let me collect your data, your GPS, let me use your GPS and collect the data. So, I have the people who are going through various commuters, and they collect those data, and from that they are building a road network, right. Now, you do not want to show the road network as those points set for the top thing, because you want to generate the roads. So, now I have, when I have connected those points and I got the trajectory, how do I build the road? And you do not want to throw away most of the points except the few points that you want to keep. So, that also comes to this question about the curve simplification. Other way of sort of saying is this is a form of data compression. There is a conflict, inherent conflict between accuracy and efficiency. The more information, more data you have more accurate representation, but it takes more time to process it. So, how much loss I am willing to give to speed up my algorithm? So, there are whole different ways of doing it. The second is because a GPS, when again let me go back to GPS example, when you are going on a road in GPS has some statistical error, some measurement error. So, even if you are going on a line, the points that you will get will not be a point on a line, it has some error, and so you will get a wiggly line. What you would like to do is you would like to clean it up and give me a straight line. So, again that is basically I want to simplify the curve. So, next in topic on line is curve or surface. Let me talk about the curve first, then I will talk about the curve surface simplification. So, the problem is the following will be, so either you have you can think about that I have a sequence of points. So, okay, and what I would like to say is I will give you a tolerance error. So, epsilon error. What you want to do is that, so this is at P, choose a subset Q of P. So, let us say Q is, so P, let us say P is P1 Pn, Q is let us say Q1 Qk. So, that if you connect, let us say so this is Q1, oops, Q2, so on, and you connect it, let us say, then so then each Pi lies within distance epsilon from the chain Q1, Q2, Qk, right. So, basically what it says is that all the points lie very near this polygonal chain. So, suppose if you have a so you draw this so you draw this buffer zone of error epsilon around this chain, all the points should lie inside this in this buffer zone, okay, all right, and k should be small, because so this is a you can of course talk about return me a I give you the set P, I give you epsilon, return me the smallest size q, so that all the points lie within distance epsilon from this polygonal chain. Okay. So, this is a goal. Now, there is a dual problem also, that you may have fixed budget, right, because let us say that I can give you only 3, you can store only 3 points, and then find the 3 points, so that the error is as small as possible. So, this is called minimum k problem, that I give you an epsilon, find the smallest k, or the dual problem will be I will give the value of k and choose a k points, subsets of the points, input points, so that if you connect them, then the error is as small as possible. Okay. So, let me give you first 2 popular techniques that are used, and then I will talk about what is the theoretically known. So, there are 2 general techniques that are used both for curve simplification, and those methods also extend to surface simplification when we talk about 3D. Oops. So, the two methods are called approaches are called refinement, and the second one is called decimation. Now, but it occurred to me that I should also say that these problems also arise in machine learning, because what machine learning people also want to do, one of the problems is they have is that you have a lot of examples, and from those examples you want to generate very simple concepts that capture all the examples. The classification problem, a lot of they do is, and I will not have time to talk about the relationship, but a lot of this also boils down to this simplification problem. Okay. So, as the name suggests, refinement is that what you do is you start with very coarse representation and you refine it until the error becomes at most epsilon. And the decimation, you start with very dense representation and slowly you gradually keep on coarsening it until you cannot do it anymore, because error has become more than epsilon. So, let me give you the refinement method, and this is a popular heuristic method called, there are many of them, but I am going to just give you one of them, that is called Douglas Riker algorithm. Douglas Riker is pretty simple. So, here is a set of points. For example, you have what you do is it is a recursive algorithm which you do the following. Take the first point, let us say P1, let us say Pi, because since I want to define recursively. So, you have subsequence of points Pi to Pj, connect this try to connect them by a single segment. Okay. And now check if all the points between Pi and Pj, they are within distance epsilon from this segment. Okay. If that is the case, if all of them are within distance epsilon, nothing to do, you can just return that segment. Now, in this case they are not. Okay. Then what you do is, then you need to break this segment, one segment is not enough, then you need to sort of need more than one. So, you need to split this point set at some point, and what do you think is a natural choice? What do you mean median?
Which point is the point which is at the most distance?
Yeah. So, intuitively basically one way of you can come up with a different method, but is well, since you are looking at the geometric error, so take the point where the geometric error is the most. So, take the point that is farthest from this segment. Let us call this point, let us say this is a point, and do Pk, and now you recursively solve this problem at this peak. So, you do not add this segment, you try right, and now continue doing it. So, suppose this is also not good enough, then this is the point, and maybe here you have in the left side you are done, because this is within distance epsilon. So, you stop here, but let us say here you will take this point, let us say, and you can do, and let us say these two segments are enough, and recursively you will do it here, right. So, that is the algorithm. It is pretty simple algorithm, and it is used quite a bit in the practice. It is one of the most popularly used methods for curve simplification, refinement method. What is the running time? So, k, well, I do not know the value of k, I mean, right. So, what in the worst case k can be as large as n, if you are really unlucky. So, you are right. So, in the worst if I do it naive implementation, it will be, because at each step what I need to do is I need to figure out, look at all the points within distance and see whether it is within distance epsilon. So, you spend linear time. Now, if you are unlucky and recursive call is very unbalanced, it is like quick sort, then the worst case running time can be quadratic, or if it is a final size output size is k, it could be k times n, right. Now, by being more careful, and using some data structures which I will not talk about, you can make sure that the running time is always n log n. Okay. But it is not known what is the lower bound. Okay. So, it is not known whether the lower bound is n log n or whether one can do linear. There was a paper which claimed n log star n algorithm for this problem, but I believe it has it never appeared in a journal, it was in a conference. I believe it has some technical issues. So, it is not known whether whether you can implement this algorithm better than n log n time. N log n is not hard, you require some, let me put this way, you can do it. If I give you a final problem, you should be able to do it, exam problem, because it does not need more than what you have learnt in this class. Okay. So, this is an example of refinement method. Any questions?
Is there any guarantee on the k?
No.
Right,
no. So, yeah, that is the other issue, is that which I was going to say come later, is the algorithm does not necessarily give you optimal what the minimum value of k, because you can ask the optimal question that for given value of epsilon what is the smallest value of k, and you can construct an example where it will do really bad, that there is a constant size output, but it gives you the almost linear. So, it is not only optimal, but it is not nowhere near optimal in the worst case, but in practice it does very well, and that is why people use it, because so it is simple to implement it. You can also implement it in a more sort of, it does not require any space much, and you can do it in online manner, you can do it in distributed manner. There is a lot of nice things one can do with it. No, once I finish, then I will give you an algorithm which is optimal. There are some versions of it that are not known to be in P, which if I have time I will talk about it. Okay, so let me talk about decimation method. So, decimation method is you want to start with all the points and slowly throw away one point after another. Okay. So, these are all the points, am I right? If I want to throw points one after another, what do you think we should do? Yeah. So, the error is at most epsilon, then you can throw it. Now, since if I want to do the incremental error way, want to throw point of, in what order should I throw away point? There may be many points, they may satisfy this. So, that is one way of doing it. You do start from scan left to right, for example, that is one way of doing it. You start from left to right, and let us say I start from here, okay. And the question whether I need the second point. So, as you said, you connect to the third point and see if this error is here, I can sort of throw it away. Now, if I can throw it away, then that is fine, and I stick to this. Now, if I ask a question whether I want to do this, whether I can do this, you can. So, that is one way, is doing from left to right. Other way of doing it is, in some sense, think about the reverse of this original Douglas-Piker stuff. What you do is, what you think about it is, here what I did was I had a segment, I split the segment into two segments, that is what I did, right. What you can do is, you can take the two consecutive segments and see can I fuse them to a single segment, and you fuse them if the error introduced is not more than epsilon. Okay, so, that is what you can do. So, that is called edge contraction, because you are taking two edges, contracting them to a single edge. Now, again, in the worst case, this may take n square time, and but again you can, by being a little more careful, you can implement it in n log n time. again this has the same problem as a Douglas-Fokker in the sense that it does not guarantee that it returns anything near optimal, and it may return again pretty bad output in the worst case. Okay. So, but both of these heuristics are used quite a bit in practice. So, let me sort of say, let me call it optimal algorithm. Now, one thing I should say, I have been doing some cheating here. If you look at the pictures I have drawn here, all this, for example, if you look at this picture that I drew, then if you look at this picture and look at the third picture, these are all x monotone curves, but the picture that I have drawn here is highly non-monotone, and no one has asked me the question, because and it is deliberate, it is not accident, because when things are not monotone you run into some problems, and I will address that later. So, for now I will continue to assume that the points are x monotone. So, basically if you increase the index, x coordinates are monotonically increasing. So, what I am going to do is the following is, so again this is set P, it starts with P1, goes all the Pn. Now, what I am going to do is I am going to construct a graph whose vertices are points themselves, and you have set of edges. So, a pair Pi Pj belongs to E if distance from Pk to the segment Pi Pj is less than epsilon for all. What I am saying is basically, if this is Pi, let us say this is Pj, you have an edge in the graph if all the points from Pi to Pj they are within distance epsilon from the segment, right. So, you construct a graph. Good question. So, what I mean by optimal algorithm is return me the given a epsilon, return the polygonal chain with the fewest number of edges. So, optimal in terms of k.
And you are limited to using the
yes.
points.
Yes. Okay. So, now if I construct this graph, what should you do to reconstruct the curve with the, how do you solve the problem? Pardon? Say it, I can't hear you.
Dynamic programming. Use dynamic programming and construct the curve.
So, you can maybe you can say somewhat like, yes, it will, you can do dynamic programming, but you can give me one line, you can reduce it to some. Yes, you want to find the shortest path with minimum number of edges from P1 to n, right, that has minimum number of links. So, find the shortest path from P1 to P. So, how much time will this take? What is the running time of this algorithm?
So, for constructing a graph, the order is n cube.
Yes.
The n square is n for each.
That is right. So, the worst case running time, if I do naively, it is n cube as you said, because the n square pairs I need to check, for each of them I do linearly. Now, one thing so n cube is pretty straightforward, am I right? Is it clear to everyone, or I should explain why n cube? So, n cube is pretty straightforward. Now, can you reduce it to n square log n, or n square roughly? Actually, you can reduce it to n square or n. I don't care about the log factor. I just want to hear some idea that you can bring it down to n square. So, somehow you want to construct, you do not want to construct. So, think about the following. Right now what I am saying is the way you get n cube, that you are constructing n square edges, am I right? And you are saying right now I spend linear time on each of the edge. But do we have really to spend linear time to construct each edge? So, you think about all the edges, let us say, which are going from pi to the higher side, right? Pi to pi plus 1, pi to pi plus 2, da da da. I am repeating a lot of work if I am going to spend linear time, right? I should be able to reuse the work I have done. So, how would you do that? So, think about the following, and let me give you a hint. So, here you are starting with pi, and here are these points. What does it mean that all these points lie within distance epsilon from the segment which I try to draw? Or ask the following question: what is the set of segments or set of rays? So, I am thinking about things which are going to the right, am I right? What is the set of rays for which the distance from all these points is at most epsilon? Am I right? Because that is what you want to ask the question. Because the condition is that you want to connect them by segment if and only if all the points they lie within distance epsilon. So, what you do, think about is you draw the disk of radius epsilon around each point, and if the line that starts from here, think about a line, so that all these points are within distance epsilon from that line. What does that mean? All that disk should intersect this line. Okay. Now, if I ask the following question, look at the line. What is the set of lines that intersect all these disks? So, for example, think about the following this way. Well, there may not be such a line, it might be an empty set, but suppose if there is such a set. Well, actually in this case there will not be a set, but let me make it little simpler. So, this line, if you take the vertical line, that does not intersect any disk. Now, I start rotating it around this point, am I right? At some point it will become a tangent, but it still does not, its tangent, it starts intersecting this one and does not intersect this one. Now, if I, and then I continue doing it, it will continue intersecting it, it will intersect something else. So, this happens at this point, right. And look at the first line when you continue the rotation, the first line ray that intersects all the disks. So, that will be something like this, all right. So, this is a line that this intersects all the disks, and that is the first such line. And what will be the last such line that will happen?
So, all the disk has to be within the two tangents that are in the first circle, right?
No, that is right. So, what you, yes, you are stamped, right, that is true, and not only that is true for this is true for each such circle, am I right. So, what you want to do is you have a cone, am I right. So, the next will be something like this, that will be the last line. So, what you do is you have these cones, as you sort of said, for each circle you draw the two tangents from this point pi, and these are the cones which have the same apex, and if you look at the intersection of these cones, this itself will be a narrow cone. Okay. So, this is this set of lines. Now, when you add another one, you will get another cone, and you take the intersection of these two cones. So, if that cone remains non-empty, it means you can add this edge and at some point this cone will become empty, then there is no such line and you do not have to put the segment. So, that is all you have to do. When you maintain this cone, the starting point, whenever you add a and you start marching the points from pi to the right onward, and you maintain as long as the cone remains empty, non-empty, you add that segment, and when it stops, then you basically stop adding that. So, you get this edges. So, you get this. So, this way you are spending only constant time at each point, maintain the cone. So, it takes n square time total. So, you can construct this graph. Now, the question is, can you do better than n square? Now, this graph is not arbitrary, am I right? Because you have the edges going from pi to pi plus 1, pi plus 2, there is a subsequent graph. So, this graph has lot of a structure.
No, so there may, you said constant time, but that also depends on the number of circles, right? You are assuming the number of circles are here.
So, okay, so if you go from pi and start pi plus 1, go pi plus 2, every time you add a disk, you are spending constant time to add a disk, right? So, if you, so yes, so in the worst case I will spend linear time. So, in the linear time I can add all the edges that whose left end point is pi, and then I repeat it for every point. So, the total time will be n square. Now, but this graph has a lot of a structure, it is not an arbitrary graph. So, it is no reason to say that you have to represent, you have to spend n square time to find the shortest path in this graph, okay. And it is not known whether you can do better than n square. So, that is a nice theoretical open problem. Now, if I change the rule of the game slightly differently, which is used a lot, that suppose these are the function values that you sampled, and if it is a x monotone curve, it is a reasonable stuff to assume it is a functional sampling of function. Then what is called the Chebyshev metric? This is called Hausdorff metric. The Chebyshev metric is that you replace, instead of thinking about the disk, you think about I just care about the function value at that point x. So, I replace this disk by vertical segments, and then again the condition becomes this line should intersect all these vertical segments. That is called Chebyshev metric. So, you are looking at the error under Chebyshev metric doing it, and then it turns out you can do better. Then you can find the shortest path in time n to power 4/3. So, there is a subquadratic algorithm, but when you look at the Hausdorff metric, it's there is no subquadratic algorithm known, and that is it would be nice to understand what the real right bound is. There have been a number of erroneous papers on this problem. So, just want to sort of people sort of came up with some condition and that turns out to be false. So, in terms of time optimality, we do not know what one can do. Any questions? So, now let me sort of, I am running out, I am going to run out of time soon. So, let me talk about surface simplification.
Graph that you constructed is an unweighted graph, right? You just
yes, unweighted graph, that is right. So, minimum number of edges. Now, before I talk about surface simplification, I should say the following. I should say the remark I made about this monotone versus non-monotone. Now, what happens is that you start with a simple polygon, am I right? But what may happen is that if you had something like this, and if you replace this by simplify, suppose error was large, you simplify, then what will happen is you may get something like self intersecting curve. So, it is no longer intersecting, it is not no longer, you started with a simple curve, simple polygon, but once you simplified it, you got a self intersecting curve. And finding an optimal algorithm, so what is not known is whether you can compute a non-intersecting curve which is the smallest size for a given epsilon, whether it's whether this problem is in P, that is not known. As far as I know, it is not known to be in P. Now, if I talk about surface simplification, so now both of these methods, refinement and decimation method, they can be extended to surface simplification. And here is what you do is refinement method is, let us say that all the points lie inside a triangle. Okay. So, you have a, it is not a, if that is not the case, there are many ways of circumventing this problem. So, what I mean by is that I take the points. So, now if your surface that points are sitting in 3D, you project them on the plane, okay, and let us say all the projections lie inside a triangle. Okay. Now, in the case of Douglas-Piker, what we are doing is the question we are looking at the first and last point. Now, there is no sequence, am I right, but there is sort of will be a kind of an ordering, and you ask the question whether the segment approximated all the points. Now, I will ask the following question: take these 3 points, the triangle, whether this triangle approximates all the points, with all the points inside this triangle, whether the distance epsilon from the triangle, let us say vertical height. So, you took the 3 points, you have the triangle. So, this the triangle is suspended in 3 space, and you have all these points whose projections lies inside this triangle, and you ask whether this distance is at most epsilon. If it is the case, then this triangle approximates all the points, you are fine. Otherwise, you do the same as Douglas-Piker. Take the point that is the farthest from the this triangle, and let us say, and what you are going to do is you can going to replace, let us say this is the point, you are going to replace this triangle by 3 triangles. So, it is easier to think in terms of the projection, that you have the projection here and solve the problem recursively for each of these 3 triangles, and then you can take this point and map it back in the 3 space. So, you start with 1 triangle, replace it by 3 triangles, and you ask the same question, and you can keep on doing it until you find you reach a triangle, so that all the points lie within distance epsilon. So, that is a straightforward extension of Douglas-Piker algorithm in 3D. I will not go into detail, this is not used a lot in practice in 3D. What is used in 3D is a lot is the decimation method. So, what now happens is the following, and you think about with the projection, because it is easier to think about the. So, if you take this, so what you do is you have a set of points. So, here is algorithm, you start you have a set of points in 3D, but they are following a surface x mono y monotone surface. Project them on the plane, compute a Delaunay triangulation, and lift it back in 3D. You get a surface. And instead of thinking about the in 3D, thinking just with the Delaunay triangulation itself. So, you have a set of points, which was a projection of the points from 3D, and you constructed the Delaunay triangulation. Let us say this was Delaunay triangle. Now, it is not sort of polygon chain that you just take 2 consecutive edges and do it. No, but there is a notion of edge contraction here also. So, think about, let us say I want to contract this edge. So, it has 2 endpoints, vertices, you fuse them to a single endpoint. So, let us, it is to make sense, you think about A, B, C, D, E, F, G. So, these are the neighbors of A and B. Once you fuse it, A and B sort of becomes contracts to a single point. Then what happens is that these 2 triangles, which were adjacent to the edge AB, they get fused and they become 2 edges. So, let us say this is a fused vertex A B, then you get C, you get G, then you have this D, E, wait, not sorry, not G F. And the rest of the graph will remain the same, right. I hope this is right, I did not make a mistake. Yeah, it seems right. Okay. Now, there are many questions here. Where should this fused vertex sit? And the simplest thing is you make it either sit on A or you make it sit on B. Okay, so either think about you bringing this vertex here or you think about bringing this vertex here. Okay, happens. And now what you have to say is basically you lost one vertex, the two vertices become one vertex, and you check the, so this vertex which let us say you bring it to point A, then the vertex B lies somewhere. And you check what is the now distance between B and the triangle. If the error is at most epsilon, you do this contraction. If it is more than epsilon, then you do not do this contraction. That is what you basically rule. And this has been used enormously, this simple heuristic, in practice. And again, since the question is which one you should do next, you basically maintain in priority queue what is error and pick up the vertex which introduce the minimum error and contract that edge, and then you keep on doing it, repeating it. There is a publicly available software for this problem, and this was all the heuristic has been defined earlier, but this is known as Garland-Hagbert algorithm, because they are the one who did very nice present. They are the one who gave up a lot of nice details, algorithmic details, and also the implementation, and you can get the software from their web pages. There are many different extensions of this algorithm. Now, let me go back to the question of the optimal algorithm, which I talked about 2D, that if I give an error epsilon and what is the minimum number of triangles, now the question you ask is, so you can get the representation. And that's surprising, the problem is not known. People suspect it is an NP hard, but the proof seems to be even harder to prove that it is NP hard. And there are a lot of people have worked a lot on to prove that this problem is NP hard, and not only that, there is no approximation algorithm known also. So, suppose I tell you that if I give you an error epsilon, there is a surface with the k triangles that has error at most epsilon. Can you generate a surface with k log k triangles or even k square triangles or even k cube triangles? Nothing is known. What is known is the following: if you do not insist that the vertices of the triangle should be the input points, then there are approximation algorithms. But somehow if you insist that the vertices of the triangle should be the subset of the input points, then nothing is known, no approximation algorithm known, it is not known whether the problem is NP hard, and they are doing measurements. And now you want to have a sparse representation to basically of this surface measurements of sensors, and then you question is, and also it is not a centralized computation, because you do not want to send all the data from sensors to the base station, you want to do local computation. So, the question is there a distributed algorithm to do such a surface approximation, and that is also an open problem, it is not known, you can do it. So, let me stop here.